Hi students, welcome to class. We will be beginning Chapter 8 today, and in Chapter 8 we were going to be studying rational and radical functions. And hopefully we'll learn everything you ever wanted to know about rational and radical functions. We're going to be starting with rational expressions and talking all about rational expressions. So what is a rational expression? Well, an expression that's a rational expression is a ratio of two polynomials. And it's called a rational expression because one is divided by the other, like in a ratio. So rational really stands for a ratio between these polynomial expressions. Our learning goals for today are to simplify rational expressions and to multiply and divide rational expressions. Let's take a look at a few rational expressions. So again, a rational expression is a quotient of two polynomials, and here are some examples. X squared minus 4 divided by x plus 2, that's a rational expression. It's got two polynomials are being divided. We have 10 divided by x squared minus 6, or x plus 3 divided by x minus 7. And you can simplify rational expressions the same way as you simplify fractions. How do we write a fraction in simplest form? For example, how would we simplify the fraction 4/8? Well, when we think about 4/8, we think about, well, the numerator and the denominator have common factors. They both have a common factor of 4. So we think about the greatest common factor of the numerator and the denominator, and basically what we do is we divide that out of both the numerator and the denominator, and what's left over is a fraction that would be in simplest form. So in general, how we simplify a fraction is by dividing out the greatest common factor of the numerator and the denominator. Also, a quick note, it's really important to remember that when there's a 0 in the denominator, the fraction is undefined. So we always say that a fraction would be undefined when the denominator is 0 because we can't divide something up into 0 parts. So if you were to have a variable in the denominator, you must make sure that you consider any situation that might make that denominator 0. So you have to consider what value that someone might input in for the variable that would cause the denominator to be 0, and you have to exclude that value from the domain. So we'll just say, in some cases, well, x cannot equal these particular numbers that make the denominator equal to 0. So remember, our first learning goal was to simplify rational expressions, and so our first example is just that, simplifying rational expressions. Let's take a look at example A. This probably looks very familiar. We've done a lot of work with this type of rational expression as we studied the exponent rules. And so if I wanted to simplify 10x to the 8th power divided by 6x to the 4th power, the first thing I do is I would think about splitting the numeric parts up and then the parts with the same bases, the numerator and the denominator. Now when I reduce a numeric fraction, I'm just looking for the number that can divide in the numerator and the denominator evenly, and of course we know that in this case that is 2. So we could divide a 2 out of the 10, making it a 5, a 2 out of the 6, making that a 3, and so that part can simplify to 5/3. Now with the variables, we think about the bases are the same. The rule for exponents says we subtract the exponents. But it might be even actually easier to think about just doing some canceling. We know that we really have 4 x's on the bottom and we have 8 of them on the top. So if we were to cancel out all of these x's on the bottom, then we would only have 4 left on the top. And so that's really an easier way to look at that when we're dealing with simplifying these rational expressions with variables. So we think about more like canceling instead of necessarily subtracting the exponents. So that leaves me with 5x to the 4th over 3. Now, as I said before, we have to think about what might have made this expression equal to 0 on the denominator, and we have to exclude that. Well, think about what the denominator was. The denominator was the 6 x to the fourth. And what would make that 0, the only value that would make this 0 is actually 0. So what we do is we actually say that x cannot equal 0, because if it were 0, then it would make the original expression undefined. So in addition to simplifying this rational expression, we also have to just restrict the domain and say, well, x can never be 0. Okay, so how about example B? Well, this is asking us to divide two polynomials. Now, we've done some dividing. We've done dividing with long division. We've done dividing with synthetic division. And now we're going to look at using factoring to divide and reduce a rational expression. So if we look at this rational expression as two separate pieces first, and we just kind of focus on the numerator and the denominator, we could take each of these parts and factor them. So I have on the top x squared plus x minus 2, and when I think about factoring, it means I'm doing reverse FOIL, as we talked about reviewing our factoring skills. And so what I'm looking for is I'm looking for two binomials that multiply to give me x squared plus x minus 2. Well, first of all, I know they're both going to start off with an x, because x times x is x squared. But next I have to think about what two numbers will multiply to give me a negative 2. So they have to multiply to give me this negative 2, and they have to add to give me this positive 1. This number that's in front of the x, there's a 1 there, so I'm actually going to write a 1 right there, and so they have to add to 1 and multiply to negative 2. So I think about negative 2 multiplying to a negative number. One has to be positive, one has to be negative, and the only factors I can think of for 2, because it's prime, are 2 and 1. So I have to figure out which one has to be positive, and it'll have to be the 2 that's positive and the 1 that's negative. Then that way 2 times negative 1 is negative 2, and 2 plus negative 1 is positive 1. So that works. Now I go down and I look at the denominator. I'm going to do the exact same thing. I'm going to see what are the two binomial factors of x squared plus 2x minus 3. So I know they're both going to start off with an x. They have to multiply to give me this negative 3, but then they have to add to give me this positive 2. So I think of factors of negative 3. One will be positive, one will be negative, because to multiply to give me a negative, I need to have one of each sign. And they have to add to a positive 2, so that means the 3 is going to have to be the positive, and the 1 is going to have to be negative. And again, 3 is prime, so there's only 3 and 1 for factors. So now when we go back and look at this as a whole now, and not just a separate numerator and a separate denominator, but together as a ratio, you can see that there is a common factor in the numerator and the denominator. There's this x minus 1 on the top and the bottom that we can just go ahead and cancel out. And so that leaves us with x plus 2 on the numerator and x plus 3 on the denominator. Now we said that we have to make sure that this expression is never undefined, and so we have to exclude the values that would make it undefined. Now when we do that, we actually want to do that prior to any canceling. So we really want to go back and look at the denominator before we canceled anything out and see what would make that equal to 0. And so we know that what would make x minus 1 equal to 0 is a positive 1. If I plugged in 1 for x, that would make that 0. And I know that what would make x plus 3 equal to 0 would be negative 3. So my two exclusions for my x values are negative 3 and 0. So x cannot be negative 3 or 1. I might have said 0. I bet negative 3 or 1, sorry. So again, as a note, we want to make sure that we consider the denominator before we do any canceling out, because we don't want to miss a possible value of x that would make it undefined. Let's go ahead and turn the page. Well, this time the denominator is a little trickier to factor because remember it doesn't have a leading coefficient of 1. And so this is where we have to pull out that AC method. So we're going to try to factor this 3x squared plus x minus 4 using the AC method. So our A is 3, our C is negative 4. When we multiply 3 by negative 4, we get negative 12. So that's 3 times negative 4. So what we're trying to do is to find two factors of negative 12 that will add up to the middle term. Well, notice that the middle term is 1. So there's not anything in front of the x, so it's 1. So I got to think of two things that multiply to give negative 12 that add to give positive 1. And right away, I think about the positive 4 and negative 3. So they would multiply to give negative 12, but they would add to give positive 1. So then what I do is I rewrite this trinomial as a 4-term polynomial. And I do that by keeping the first and the last terms exactly the same. And instead, what I do is I break that middle term down into two separate pieces. And it doesn't matter which one goes first. You can put either 4x or negative 3x first, but I kind of have a feeling it worked best if I put the minus 3x first, because then it's by the 3x squared, and then the minus 4x. And the reason why we do that is now that we have a 4-term polynomial, we can split this up and do our factoring by grouping. So if we take the first two together and we take out the greatest common factor, we could take a 3x out of that, and that leaves us with an x minus 1. Do the same thing for the second pairing. I could take out a positive 4 out of both, and that leaves me with an x minus 1. Well, then that means that one of my factors for this polynomial, I'm going to go up here and write it, is the two numbers that are out in front. Remember, these two go together to make one of my binomials, and that's 3x plus 4. And then the other factor is the greatest common factor that you see there, the x minus 1. And so this factors down to 3x plus 4 and x minus 1. And then remember that the numerator was 3x plus 4. Well, if there's a 3x plus 4 on the top and a 3x plus 4 on the bottom, we can simply cancel those out. Well, what's left on the top? Well, just a 1. So this actually reduces down to 1 over x minus 1. And so that would actually be the simplification of this. But then being able to tell what the denominator cannot be, what x cannot be, because it will make the denominator 0, I have to look at that factored form before I canceled, and I think about what would make that equal to 0. Well, 3x plus 4, if I set that equal to 0, and I solved, I would have to solve by subtracting 4 and dividing by 3, so that would give me a negative 4/3. And the other thing that would be make the denominator 0 would be whatever makes x minus 1 equal to 0, and that, of course, is 1. So the two values that I cannot have for x are negative 4/3 and 1. So my answer would be 1 over x minus 1, and the exclusions on x cannot be negative 4/3 and also cannot be 1. Okay, so it is time for a you try question. Example D is partially factored for you. They already factored the numerator for you. You're halfway there. All you need to do is use the AC method to factor the bottom, and then find out what values x cannot have that would make the denominator 0, and then reduce. So please pause the video now, try that one, and then tune back in to check and see how you did. So how did you do? If for some reason you didn't get the answer 2x plus 1 over 2x minus 3, and that the two values that x cannot have are negative 2/3 and 3/2, please pause the video and look through the work and see if you can figure out where your error occurred. And also, you may make note on your guided notes and bring that up when I see you in class. Let's go ahead and move on to the next examples. So I look at this next example, and right away something kind of jumps out at me about the numerator in example A. So we're asked to simplify, identify any x values for which the expression is undefined. And if you notice, the example is entitled Simplifying by Factoring by Negative 1. So you'll see where that kind of comes into play in just a second. But what I noticed right away is the numerator, 4x minus x squared, is not in the typical form I see it in, which is descending order of powers. So the first thing I'm going to do is rewrite this so that the x squared part is first. So I'm going to have to switch these around, which makes it negative x squared plus 4x. And the denominator is fine. It's in the correct order. It's got the x squared, then the x, and then the constant term. So now I'm going to go ahead and take a look at the numerator and see if there's anything I can factor out. Well, right away, I see that the leading term is negative. I never want that to be the case. And really, other than that, that negative, the only thing I can really take out of both terms, and when I think there's two terms right away, unless it's a special factoring pattern, I think right away about just greatest common factoring. So I'm looking for the greatest common factor that I can take out. So I actually could take out a negative and an x out of the numerator, and if I did that, I would be left with an x and a minus 4. So x minus 4 times negative x would actually give me that negative x squared plus 4x. Now I'm going to go ahead and take a look at the denominator and see about factoring that. So that's a fairly easy one to factor. The leading term is 1. And so I know that both the x, the binomials are going to start off with x. And now I'm looking for terms that multiply to give me negative 8, that add to give me negative 2. Right away, I know that that means one of them is going to have to be negative and one's going to be positive. Now the one that's going to have to be negative is clearly going to have to be the 4 because I needed to add to negative 2. So that way I have negative 4 times positive 2 is negative 8, and negative 4 plus 2 is negative 2. So that works out. Now before I start doing any canceling, I'm gonna see what things the denominator, the value of x cannot be to make the denominator 0. So I know right away that I can see that this one right here, 4 would cause that to be 0. And then the next one, that x plus 2, well, I know that that means x cannot be a negative 2 because plugging in negative 2 for x would make that 0. So I've got that taken care of. Now I can worry about doing this canceling that I like to do. So I'm going to see what's common in the numerator and the denominator. So I have x minus 4 and x minus 4. I could just cancel those right out. That leaves me with a negative x on the top and an x plus 2 on the bottom. And that is my simplified expression. So let's go ahead and make b, which seems to be the easier of the next two. We'll make b the you try question. So think about the numerator, make sure it's in descending order of powers. If not, switch it around. And if there's a leading term that is negative, or if there's greatest common factor, factor that out. So go ahead and pause the video now and give example B a try. Okay, so that example really gives new meaning to simplifying. That definitely simplified the expression all the way down to just an integer of negative 2. Want to make sure that you also indicate which values x cannot have, the ones that actually make the denominator 0. We don't really care if the numerator is 0. The numerator of any fraction can be 0, but the denominator can not be. And so that's why when we're evaluating these x values that make this undefined, we simply look at the denominator. We don't really care about the numerator in terms of what would make the function undefined. And I saved example C for us to do together. Example C requires us again to do a little more complex factoring. So let's take a look at the numerator. So if we look at the numerator, negative x squared plus 3x. First thing I think about, two terms. I know if it's two terms, then I'm going to, if it's not a special factoring pattern like sum or difference of cubes or difference of squares, then I know really the best I'm going to be able to do is get out a greatest common factor. So I can see that I could take an x out of both terms, but because my leading term's negative, I want to really take out a negative x to make that first term or that leading term positive. So when I take out a negative x out of negative x squared, that leaves me with a positive x, and when I divide it out of positive 3x, it leaves me with a negative 3. Now look at the denominator. So the denominator, I'm going to have to use that AC method on again. So A is 2 and C is 3. So 2 times 3 is 6. So I'm looking for factors of positive 6 that add to negative 7. Well, if it's positive 6, then they both factors either have to be positive or both negative. But since they have to add to negative 7, I'm thinking right away of two negatives. And I can think of negative 6 and negative 1. They'll multiply to give me that positive 6 and add to give me the negative 7. So I'm going to take this and I'm going to rewrite it as a 4-term polynomial, keeping the first and the last terms the same and splitting the middle term into 2 separate terms of negative 6x and negative 1x. And again, you can put either one first. I'm going to go ahead and put the negative 1x first and the negative 6x next. And then we split down the middle and take 2 and 2 and factor by grouping. So I look at the first pairing. I can factor out of 2x squared and negative 1x. I can take an x out. So I'm going to do that, take an x out. That leaves me with 2x minus 1. And then when I look at the negative 6x plus 3, I see that my leading term of that grouping is a negative. So I'm not only thinking about what can I take out of 6 and 3, but I'm also thinking I want to take a negative out. So I actually want to divide out negative, and then the greatest common factor of 6x and 3 would actually be 3. So I'm going to take a negative 3 out. And so I'm going to divide both of those by negative 3, divide negative 6x by negative 3, I get positive 2x. Divide a positive 3 by negative 3, I get negative 1. And there, now I have that greatest common factor, that common binomial factor right there. That means the factored form of this is x minus 3, the numbers out in front, and then the common binomial of 2x minus 1. So before I do any canceling, I'm going to take a look at what would make the denominator 0. Well, a positive 3 would make this first binomial equal to 0. And then looking at the next one, 2x minus 1, in order to, if I set that equal to 0, I'd have to add 1 and divide by 2, and that gives me a positive 1/2. So I know 3 and 1/2 are both going to make this undefined. Now I can do my canceling. Cancel out x minus 3 on the top and the bottom, and I'm left with just negative x on the top and 2x minus 1 on the bottom. So that's my final simplified form. Now, one thing real quick to note, when we multiply rational expressions, there are still the issues of the denominator, if it's 0, making the expression undefined. But because our calculations tend to be pretty complex, we sort of just put that on the back burner. We just choose not to worry too much about the denominator and what makes it undefined. But just keep that in the back of your mind that that is still an issue. We're just not going to ask you to tell the values that would make it undefined. So let's take a look at our first example. Now with something like example A, where we have just these monomial polynomials in our separate rational expressions, my suggestion would be to do this first of all. Don't start trying to do canceling and reducing. My suggestion would actually be to go ahead and multiply the numerators and multiply the denominators first. So go straight to step 3. And the reason why is you start cross-canceling across the fractions and all that, it gets kind of complicated. So it's kind of easier if right now we just combine and put everything that we can put together first and then reduce at the end. And so that's what I'm going to do. I'm going to go ahead and multiply the numerators, and I'm going to multiply the denominators. So when I multiply the numerators, I'm multiplying the constant terms of 3 and 10. They multiply to give me 30. The x to the 5th I can multiply by the x to the 3rd, and when we multiply two bases that are the same, we add the exponents. And so that's going to be x to the 8th, and then y to the 7th. Now the denominator, if I multiply the 2 and the 9, I get 18. The x to the 3rd and the x to the 2nd is x to the 5th, and the y to the 7th times the y to the 5th, that's y to the 12th. Now you can kind of think about these as just sort of splitting them up like the numbers and then the like bases and just reducing from there. So if I think about the 30 and the 18, I know that I can take a 6 out of both. I can take a 6 out of 30 5 times, a 6 out of 18 3 times, and so I know that reduces to 5/3. And then I think about, I have an x to the 8th on the top and an x to the 5th on the bottom. If I cancel all these on the bottom, all these x to the 5th, I have to cancel 5 of the ones on the top, and that just leaves me with an x to the 3rd left on the top. With the y's, well, there's more on the bottom than on the top. So if I cancel all these on the top, all 7 of them, then I'm only left with 5 more y's left on the bottom. So my final answer looks like this. There's a 5 and an x to the 3rd on the top. there's a 3 and a y to the 5th on the bottom. And so my final answer is 5x to the 3rd over 3y to the 5th. Now for something like example B, I definitely want to follow these directions, the four stepped out directions here in this box. And so the first step says to factor all numerators and denominators completely, and that's what I'm going to do. So I look at this x minus 3. There's nothing I can do to simplify that at all. I can't factor that. So look at the denominator of that. 4x plus 20. Well, I think right away, it's two terms. The best I can really do is take out a greatest common factor. So I'm going to go ahead and do that, and I'm going to take out the 4. So I can take out a 4, and that leaves me with x plus 5. Then I go over here and I look at the other expression. I have x plus 5 on the top, can't do anything there. I have x squared minus 9. Well, you might recognize that as a difference of two perfect squares. So the difference of squares pattern works like this. The binomials are nearly identical. They just differ by the sign. One's a plus, one's a minus, and then the factors come from just square rooting those two perfect squares of x squared and 9. And so the square root of x squared is x. These both start off with x, and they'll both end with a 3. So we have one x plus 3 and one x minus 3. So it says divide out all the common numerators and denominators for step 2. Well, let's see. And I can even go, it doesn't have to just be in the same rational expression. Could be the denominator in the other rational expression. Like for instance here, we have an x plus 5 here and an x plus 5 here. Those can cancel out. I have an x minus 3 here with an x minus 3 on the top on that side. And really all that's left then on the top, because when I divide out, what I'm really doing when I cancel is I divide out, I'm left with 1s here. So that leaves me with a 1 on the top. On the bottom, I'm left with just a 4 here. See, there's a little 4 there. And then I'm left with this x plus 3. So I could write that as 4 times x plus 3, or I could write it as